And well, the next example, we will begin from the created model. Just show you how to change the analysis options to perform a dynamic seakeeping analysis with mooring. So we won't go through again through the geometry creation issues or the meshing issues. So just give me a second so we can get to the other model. See now the model again is the same model, the semi-submersible structure with the same domain, same mesh, etc. What changes now is that we have defined a different type of analysis. You remember we were previously analyzing the response amplitude operators, and now what we want to see is the dynamic response of the structure, but with mooring. So we're going to first show you how this has changed. You can see here, I'm going to mark it so you can focus on the interesting area of the data tree. You can see there what has changed. Well, first of all, you can see that the wave spectrum type is no longer the white noise. Now we have chosen the Pearson-Moscovitch spectrum. You see you have different options there. Monochromatic, white noise, which is the previous one, Pearson-Moscovitch, ion swap. These are standard wave spectrums. Also, the user could customize its own spectrum or even read from a file. You know, if you have your wave spectrum from a buoy in the sea, and you have this output, and you have it in an Excel file or something similar, you could read it from there. But in this case, we're using Pearson-Moscovitch. We have defined mean wave period, 7.7 seconds, a significant wave height of 3 meters, and well, regarding the shortest and longest period for defining the spectrum, I've chosen 3.5 and 20 seconds. This has to fulfill some conditions related to the mean wave period, which is 2.2 times for the longest period, 2.2 times the mean wave period, and for the shortest period, it should be over the mean wave period divided by 2.2. Okay, you can see here we have chosen 20 waves periods, so we have a good definition of the spectrum, and the spectrum will be spread with an angle of 60 degrees, in which we will define 10 wave directions inside this 60 degrees cone. And well, that's it for the environment in this case. Just let me delete the yellow things. And that's it. So regarding boundary conditions, everything is the same. We have the free surface and the outlet. You can draw the free surface sample. There you go. And the body data is also the same, but for the external forces. Because in this case, our model is going to be attached to the sea floor, seabed, by means of 4 mooring chains. So there's no need for these external forces representing springs. So if you go here, you can see here in the external forces, we no longer have neither the external force in the x direction and neither the external moment in the y direction, because there's no need for them. The rest of the body properties are the same, but also here you can see where previously we defined the displacement of the mass of the object was defined by the displacement. In this case, we have taken from this displacement the corresponding weight of the mooring system. It's previously calculated. You see if I can show you. It's a simple calculation. Well, you can imagine it's in an Excel file. You just get the length of the moorings and its specific weight, and you just calculate the whole mooring system weight and subtract it from the displacement. In this case, because we want the floating line to remain the same position as in the previous model. So, okay, just note down these changes. And also we have changed the time data. In this case, we have defined a simulation time of 180 seconds. It may be short, but just for showing, for this example, I think it's enough, but maybe you should need a longer simulation time. Now we are writing the results every 5 seconds. The time for recording the results is 30 seconds, and we have given 20 seconds time for the wave system to initialize. So as you can see here, this may look strange. In the time step we have left 0.0. This means that we are allowing the program to choose the correct time step related to the volume elements just below the free surface size. So this is controlled by a parameter here which is called free surface stability factor. Okay, this is a factor will assure the stability of the analysis and the convergence, and relate is the smallest size of the volume elements near the free surface with the time step. So if we leave the time step on zero, the program will automatically check this minimal size of the volume elements near the free surface and calculate a corresponding time step, a correct time step corresponding to this free surface stability factor. Okay, so the mesh is the same. You can see here. It's drawing. Second. You can see the mesh, the normal render will get a flat render so you can see it better. This is the same mesh as before. And one of the key features of this analysis is that we can define the mooring system. And so how is this done? You can see here. If you go to general data, you could see an entry which is TCL data. I'm going to mark it in yellow so you can see it here. And also I mark it down in the displayed window. You can see there. So this means we have the capability to define different mooring systems or links between different bodies floating via TCL, which is a programming code, a TCL script. So here we have defined it. I'm going to show you now the external script, the TCL script, so you can see the simple function which is used for defining the mooring system. So you can see it in the screen right now. You can see in red this commented code is just explanatory. just text explaining each of the arguments of the function used. The only real code here is right below. It is this function I'm marking now in red. It's a procedure in this script. It's called tdyn-tcl create mooring. It's a standard internal to the code, so everything is in the user manual, so you can check out there. All these functions with its arguments are defined in the and well explained in the user manual. So what is being done here is creating the 4 segments. You can see here, for example, the segment 1. See, seg 1 marked there. And the code will execute this function, tdyn-tcl create mooring segment, with these arguments. These arguments are, first of all, the type of, the body, in this case 1, just one body. If you had different bodies, you could define the mooring segment for a specific body. Let's say you have 4 bodies floating and you are going to define a segment attached to the third body. So the first argument here will be a 3. Then the second argument, this number 4 you see here, is referring to the type of mooring segment to be used. In this case, it's a quasi-static elastic catenary. And well, the rest of arguments, which I'm marking right now, are 6 numbers, refer to the coordinates of the initial and end point of this particular segment. So first you have 3 coordinates, x, y, z, for the point nearer to the floating object. So this will be the point in the leg of one of the legs of the semi-submersible structure. We'll show you later where are these points. And the next 3 coordinates, of course, are the x, y, and z coordinates of the catenary point in the sea floor. You see here, minus 120 is the coordinate, the z coordinate of the endpoint of the catenary. The next parameters are the effective weight per unit length of the catenary line. The next is the length of the segment. The next is the area, the cross-section area of the cable or the catenary or whatever. The next is the Young modulus of the material of the catenary. And for the last parameter, which we have left with a value of 0, which will mean that the catenary is fixed to the seabed point. But there are another options, so you could simulate that consider a sandy seabed contact for the catenary with the seabed, also a sliding seabed wire, and also a sliding seabed chain. So all these options are available. As you can see, 4 segments are created. I will go now to the geometry and show you which are the attaching points of the catenary to the structure. You can see right now I'm going to activate a layer with the attaching points. Let's switch off the rest of the layers so you can see correctly where the mooring system or the different segments of the mooring system are being attached. You see those 4 points. And well, the analysis would be defined with this TCL script which allows you to define the mooring system. So you just can go to the post process, so we can see what has resulted from this analysis. So we will also see afterwards the graphs for the movement, for the seakeeping movements. But in this case, it's also interesting to see the results over the sea surface. You can see now what's called here scattered waves, which refers to the reflected and diffracted waves due to the response of the object moving inside the fluid and of the diffraction of the waves when hitting the fluid. You can see here this result could be deformed, so you could see the real wave shape. This result, see here, scattered waves, and we are seeing the contour field of the scattered waves, and you can see here in the tab corresponding to the preferences, I'm going to select the result corresponding to the scattered waves. With a factor of 1. Okay, and just hit the draw button. So you could see there the waves. And of course, we could perform an animation. Well, let's hope the refresh of the internet connection allows you to see the animation. I'm afraid not, but nevertheless, I'm watching it, and it's quite amusing. And well, I'm afraid you haven't seen the animation. Well, it's due to the internet connection. Nevertheless, when you see some other result, for example, the contour field of the total elevation. This total elevation is the adding up the radiated, diffracted, and the wave system, the analytical wave system, the spectrum, the Pearson-Moscovitch spectrum we have launched towards the floating object. So now what you see is the real shape of the free surface, the sea, which is affecting and being affected by the object, the floating object. And another very, very interesting result is that we can see, of course, the displacement of the mooring. So here you see I'm going to switch off the deform of the free surface. Also, thanks to the meshes tab, I'm going to switch off the free surface layer, and we are going to see the mooring. To draw the mooring, each segment, see if we can adjust the size of the visualization of the mooring, let's say 0.5, scaling each one of them. So now I'm just scaling the view, the thickness of the view of the mooring system. You can see now the mooring system. Just going to deform it so you can see the real shape of the mooring. So I'm going back to the preferences menu. Instead of the scattered waves, I'm going to choose the displacement of the mooring result so we can see it. Just click the draw button, and there you can see the mooring system deformed with its real shape. You can see there attached to the object. You see the catenary shape that it has, its natural shape. So we could also see an animation of the movement of the mooring system. And of course we could see, as in the response amplitude operators analysis, we can see the graphs. In this case we're interested in the body kinematics result graphs. For example, let's see the heave result. Just choose it and click draw button. You can see there the movement of the structure. And well, that would be it regarding the analysis samples. Well, the only thing left is just go back to the presentation and just maybe see some more 2 or 3 aspects of the features on SeaFEM.